In this video, we're going to begin Chapter 3, which is a discussion of the analysis of variance. Now, this chapter has a whole ton of content involved with it. So this lecture set, this set of videos that makes up this lecture, is going to be relatively long to the other ones that we've done in class, just as a heads up. So the inciting question that we have here is, what if there are more than two factor levels? So in the review, we reminded ourselves of the two-sample t-test, which is a great test to use if you only have two factor levels in your independent variable. But what if there's more? Now, if there's more, the t-test doesn't directly apply. And I say directly because, well, I guess you could just remove as many factor levels as you needed to make the t-test apply, but it doesn't really innately apply. And you know what's funny is that there's a lot of situations when this comes up where we've got a whole bunch of different factor levels and many are of interest, and you don't just want to kick out the rest of them because it doesn't really fit with your analysis. And this is, of course, a case where a new analysis type comes in, the analysis of variance. And so I mentioned at the beginning of this class is not a course on analysis, this is a course on design. So what this analysis does is it's a statistical technique that, because it's around, it lets us create designs that has multiple factor levels, more than two. And in fact, the analysis of variance structure for design of experiments can incorporate just two factor levels. So if you just had two factor levels, ANOVA and the designs that are based on an ANOVA analysis framework still work. The ANOVA was developed by Fisher in the early 1920s, and again, the initial application of this is agriculture experiments, and today is used extensively in industry. And frankly, it's not just in industry. ANOVA is used all the time in social research. For me personally, one of my biggest and most well-known articles is actually a relatively simple implementation of ANOVA in a social psychology setting. So there are two different types of ANOVA, and one of the reasons that this lecture set is so long is that in our text, we address both of these as part of this chapter. So we can have a fixed effects ANOVA or a random effects ANOVA, and we're going to talk about both and the meaning differences between them, but we're actually going to start with the fixed effects ANOVA. Now I want to take a pause here and just mention to be careful about the notation. There are two notations, one that the textbook uses and then one that I tend to prefer a little bit more. Throughout, I will tend to try to align with the textbook, but there will be a few specific situations where I will use my notation because I think the textbook notation gets a little bit too confusing. I will call these out, but please be really careful and be paying attention when that happens. Maybe stick a little star at the top of the slide or your notes in that particular case. But without further ado, let's get into fixed effects ANOVA. So let's look at a textbook example. So you can look at page 70 for the example that we're going to be talking about. But let's say an engineer is investigating the relationship between the power setting and etch rate for a particular tool. That is, how fast can I make etches on a piece of metal? The objective of the experiment is to look at the relationship between these and to specifically look at a power setting that gives the etch rate that I want for a particular application. Now in this particular case, I'm going to change the power of the tool. I'm going to turn the power up a little more. I'm going to turn it down a little more. And then I'm going to observe how fast it etches. Now this particular researcher is interested in gas and gap, but we're going to fix these levels and we're only going to test 4 levels. So actually, if you remember, we're going to fix these levels of gas and gap, but we're going to test 4 levels of power. So if you remember, we previously talked about different ways that you could account for variables. One was to manipulate them, and that's what we're doing with power. Power is a manipulated variable. We're going to set it at 160 watts, 180 watts, 200 watts, 220 watts, so we're manipulating it. But the another way, not the only other way, but one other way that we could deal with this was to fix the levels of that variable. So in this particular case, we're fixing the type of gas we're using and we're fixing the distance of the gap. So we're going to test 5 wafers of metal at each of these different power settings. Another thing to notice here is that we're choosing 4 levels of power settings. But power, like the number of watts, is a completely continuous variable. So we are treating this independent variable. It is continuous by its nature in terms of power as a continuous variable, power in watts. But we're treating it as categorical for the purposes of our analysis. And we discussed in a previous video how many times when we're doing designed experiments, we don't just use a continuous variable, independent variable as continuous. What we often do is set it at particular levels so that we can have replication within each of those levels of the variable. So in this particular case, this is a great case of when we're using a continuous variable, but splitting it into categories, and actually for the purposes of our analysis, this independent variable is going to be treated as categorical. Now, because we're using 5 wafers at each power level, we're actually replicating the experiment 5 times for each level. So we have 5 trials within each level, and our total sample size, that is the total number of wafers we need, is well, if I've got 5 wafers within each of 4 power settings, I need 20 total wafers to be able to do that. So that's what we're doing. So a figure, if you're not familiar with this, frankly, I'm not familiar with this. So we have the gas supply going into the gas control panel, which then goes into this process, and then the power generator. So this is the wafer, and then we've got like a laser that's etching it on, and then we've got some discharge here. So we've got this tool that's making etches on our wafer, and we're trying to figure out how power affects it. And again, we're fixing some of these other variables, such as the distance from the etching tool from the wafer and the particular gas that we're using. Both of those could have an effect on this, and both of those are being accounted for by being fixed in the study. So we've got a bunch of different questions we could ask. Does changing the power change the mean etch rate? Does the power even matter? Is a really good question. And then, of course, recall that the main question that we wanted to ask is, how can we get a particular etch rate? So what power gives us that particular etch rate? Now, the goal of this is to have an objective way to address these questions. And note that the t-test doesn't apply here. Why doesn't the t-test apply? Because my independent variable doesn't just have 2 factor levels. The independent variable has 4 factor levels. And the t-test can only handle an independent variable with 2 levels or 2 groups, or potentially 1 level for a single sample t-test. So the t-test really isn't a useful tool for this particular study design. And again, we're going to talk about analysis of variance. That's kind of what this lecture set's about. Recall that the purpose of this discussion is to be able to have access to experimental designs that have more than 2 factor levels, because these are very common. So for the analysis of variance, what kind of data do we have? Well, typically we have a different degree of observations and some treatment levels. So the notation's going to change, but we're going to, in general, have A levels of the factor. So factor level 1, factor level 2, factor level 3. In our previous experiment, it's 160 watts, 180 watts, etc. And then in replications of the experiment, this would be what we call a balanced design, meaning there's an even number of replications within each factor level. That doesn't always happen. But when we're designing an experiment, we do tend to design balanced designs. So we've got these different observations. And ideally, we're going to run these in a random order for a completely randomized design. Little n indicates how many replications are in a single factor level. So this is very, very important. Previously in statistics, little n you've probably treated as your sample size. However, here, little n is the size within a single factor level. So we're doing 5 wafers within that factor level. But when we say little n equals 5, that means we're doing 5 wafers at the 160 watt power level. That does not mean we need 5 wafers total for the experiment. For the wafers total for the experiment, we take the number of factor levels times the number of wafers per factor level, and that gives us the total number of experimental units, those EUs. So that's capital N, lowercase n, and the book's notation stands for the number of replications. Now, what you may want to jot down here because this is a little different than what I tend to do. And again, we'll use this notation through the notes, but at one point we'll change later on for a particular purpose. But what I tend to do is capital I levels, so the capital letter I, and then capital letter J replicates. So we'd have capital letter I treatments and then capital letter J replicates. One thing you'll also know is for every observation, there is two subscripts. So Y11, Y21, etc. The first subscript is the treatment level. The second subscript is the observation. And in general, this is written Y sub ij, which is why I use capital I for the total number of levels that I could have, and capital J for the total number of options J could have. So we're considering the fixed case. We'll talk about the random effects case later. It's a little bit different than this. And the objective is to test hypothesis about the equality of each of these groups. So I'm saying, is the etch rate of each of these different groups the same? Or is in general, the mean of each of these groups the same? Now for notation, you're going to see things like this guy down here, y sub dot dot. So the dots mean when it's just a dot, it means summed over all these things, and where there's a bar, it means averaged over all these. So you'll see y bar dot dot, and this is what we call the grand mean. This is averaged over all of the i's, that is all the treatment levels, and all the j's, that is all the observations. This is the average of all of the observations. Here, y sub 1 dot bar is the average of the outcome within whatever's dotted. So in this case, it's averaged over all of the j's. Now this is kind of weird to talk about. You will get used to it over time, and we will use this notation a lot. So take some time to try to figure out what we're saying here. But y sub 1 dot is the average within group 1. Y sub 2 dot, I should say y sub 1 dot bar. Y sub 2 dot bar is the average within group 2. Y sub a dot bar is the average within group A. Y sub dot dot bar is the average across all groups and all observations. So anytime you see a dot, that means all of that taken together. So in this case, in our general y sub ij, the dot is on the j for these averages, and that means that we're averaging all of the j's, that is all the observations together within group 1, within group 2, within group A, etc. So again, the alternate notation here is for y sub ij. The I, instead of going from 1 to little a, which is what it is in the book's notation, goes from 1 to capital I, and j goes from 1 to capital J. So this is an alternate notation that I tend to prefer because it aligns the notation of y sub ij with the maximum value that those could have. But I mean, you really do get different notations all the time. So it kind of depends on what textbook you use and what paper you're reading. And I won't say that it's not standardized, but there is a degree of variability specifically about what I and J go up to. Actually, in the textbook, you'll see a couple typos where instead of going up to A like they should, the summations are written up to I. Oh, and I almost forgot to talk about one more thing. So in this data organization, you have every row as a treatment level. I will say that when I deal with data for organization of this data, I actually tend to transpose this. So what that means is instead of every row as a treatment level, I tend to do every column as a treatment level, and that's a much more standard data presentation for this type of data. At least in a wide format. We'll talk about that later too. So that is treatment level 1 would be the first column, treatment level 2 would be the second column, treatment level 3 would be the third column. And that's in direct contrast to how the book presents their data. I think one of the reasons this is how the book presents their data is to make it a little bit easier for hand calculations, like by hand, where you do it on paper and pencil with an eraser and everything. And when it's organized vertically, that makes it a little bit easier for doing the calculations on a computer. All right, so what would an example data set look like? Well, let's kind of take our example from earlier. We had the 4 different power rates, and then we had 5 observations each. Now, it's important to realize that observation 1, the first wafer I run in each power, it's not like this is the same piece of metal that I'm sticking through each one of these, right? I etch it, and then I mark it, and then I throw it away. So I don't, these aren't the same. All that they're the same in is that they, this piece of metal was the first one running 160 power. This piece of metal was the first one running 180 power. We're just saying what was the first observation within each of the categories. So be a little careful when you're interpreting that. That is not always true. There are some times when the organization is intended to describe that the same piece of metal went through all these, but recall that with our current design, that's not what happened. And again, this is where data organization and experimental design can kind of meet, because you really want your data organization to be really clear about the experimental design. Over here, we see our y1 dot bar, y2 dot bar, y3 dot bar, and y4 dot bar, and then y1 dot, y2 dot, y3 dot, y4 dot. So the totals per group and the averages per group. We can also look at, and this is something I often do, is to look at box plots. I think box plots are really useful. I tend to not do scatter diagrams as much, really leaning much more heavily on the box plots. What I see within these box plots are that as the power increases, the etch rate, also seems to increase here. And that's kind of expected. As I give more juice to the tool, it's going to work a little bit faster. And that does make sense. Intuitively with my understanding of the experiment. Now I mentioned the data format. So there's the piece that we discussed earlier, which is that I tend to put things where the factor levels are vertical, but there's a whole other thing about two different ways that we get data, and that's the long and wide format. Now in the wide format, that's what the book has displayed. And again, when I say I put each factor level in its own column, that would be considered wide format. Each column represents a factor level, each row a replication. So again, if you take some of these data sets that we looked at earlier and you transpose them, that means make the rows the columns and kind of look at it like that, where every factor level is a column, then that is a typical instruction or a typical display format of wide data. And again, this is one of the things I don't like about the textbook, because this honestly is how you're going to get data. Very, very rarely do I get data as it's presented in the textbook with a factor level per row instead of a factor level per column. So if you're going to get data that's broken out in a wide format, it's going to be with each of the columns being a different factor level typically. And if it's not, you should very likely transfer the data to be in that type of format. Now in long format, each column represents a variable, and this is a little different. And then each row represents an experimental unit. So instead of having a column per factor level, you'll have a column that says factor 1, and then the entries within that column will be level 1, level 2, level 3. And then you'll have a column that says outcome, or whatever your dependent variable is, and then a column, and then the entries are whatever that outcome is for that particular observation. So in that case, each row represents an experimental unit instead of each row representing a replication. So let's look at what this would look like. Wide format is pretty straightforward. I have factor level 1 and then all the observations when I did factor level 1. Factor level 2, all the observations when I did factor level 2. The long format's a little bit weird, but honestly, it's probably the more useful one. The long format has factor, and then I list whatever the factor was for that particular run. So let's say I have a piece of metal. So with my particular piece of metal called a wafer or coupon, then for that metal, I write down what power level am I using. I'm using 200 watts. And then I run it, and then I write down what was the outcome. And then I pick up another piece of metal and I write down, okay, what power level am I using? Well, now I'm randomly using 160 watts. And then I stick it in the machine and I write down what was the etch rate, what was the outcome. And so for this, each one of these is a different, each one represents a different coupon, a different piece of metal. And we kind of talked earlier about how with the way it was organized, it wasn't necessarily clear that observation 1 was all different pieces of metal, but when you organize it in long format, it becomes pretty explicit. where each one's a different piece of metal. And actually, the long format gives you a nice way to represent when that's not the case. If we were repeating the piece of metal, then this looks a little bit more like the wide format in a bit of a different way. And that goes a bit beyond the scope of this course, but both of these are useful. Both of these can be utilized. Typically, the long format is going to be the one that is easiest to implement in a variety of softwares. The other thing is using software. A little bit of cleverness. I don't think we talk about in our example, but you could easily look it up. An R package called dplyr, where dplyr, where you can switch back and forth between data formats. There's a variety. Reshape package, reshape to reformat. There's a whole bunch of different ones that can get you back and forth between these two. And if you get good at them, they're relatively painless. All right, so what's this analysis of variance thing? I mentioned this is a chapter on analysis of variance. What is analysis of variance? Well, analysis of variance stems from the idea of partitioning. That just means splitting up the total variability. So I've got my data and it's all mixed up. It's all variable. So the idea of analysis of variance is I'm going to split all of the movement or all of the variability in the data into two different components. One that is related to the model and one that's related to error. And we'll talk about how we do that in the next couple slides. The main benefit of analysis of variance is that we can test the difference between multiple means all at the same time. It's pretty cool. So I can, instead of having to do, let's say like a t-test between each of the different factor levels, I could test the difference between all of the different means at once. Now, this is extremely useful, but one cost here is that interpretations can be a bit limited. And if you think of a single test that looks at all the differences between all the means at once, one of the obvious questions is if it's significant, if it says, yes, there's a difference between the means. The question is, well, where is the difference between the means? I had 4 different power levels. Which ones are different from which other ones? And the ANOVA doesn't directly answer that. So we actually need some supplemental analyses to help out with that, and we'll talk about that later on. So we'll go ahead and end the video here just to keep it relatively short. In the next video, we'll pick up with a review of what statistical models are and really dive deeper into this analysis of variance idea and topic.